Right, let's solve another interesting question. It says to prove that the moment of a resistance of a beam of square section with its diagonal in the plane of bending is increased by flattening the top and bottom corners as shown below. All right, so and that the moment of resistance is a maximum when y is equals to 8a over 9. And we're also going to find the percentage increase in the moment of resistance also. All right, so you can see this is the first diagram of the square, and this is the new diagram of the square when it is cut. You can see that's why I put a dotted line here. So they inscribe a rectangle in it. All right, so we are going to start with you are going to note something first. Let's say we're going to start. Let's start with the diagonal. The diagonal the diagonal DB is equals to diagonal AC. Is equals to diagonal AC, and it is equals to what? It is equals to 2A. All right. Now, the next thing we want to calculate is the moment of inertia of this square. And if you look at this, for us to calculate the moment of inertia of the square, moment of inertia of the square section of the square, which is of the square A, B, C, D. All right. So let's name this to be what? I1. So this I1 is equals to what? Now we are calculating about the neutral axis. So we are going to have two triangles here. That is triangle ADB and triangle DBC. Same height, same what? Same base. So it means that the moment of inertia here is going to be the moment of inertia of triangle ABD. That is moment of inertia of triangle ADB and DBC. All right, so that's it. So this will be equals to, now this will be equals to 2 multiplied by, we know that the moment of inertia of a triangle about the base is nothing but what? It's nothing but BH cubed over what? Over 12. All right, so this will be equals to 2 year 1, 2 year 6, right? And the base of this triangle is what? Is 2A. So we are going to have 2A multiplied by the height. The height of this triangle, is that is A. So it's going to be A all over what? All over 6. You can see the cutoff, the height of the cutoff to the neutral axis is Y. Y for the depth of the triangle is what? A. So here we can say this is going to give us what? This is going to give us, sorry, I did not put cube on this. This is supposed to be cubed. So here 2 year 1, 2 year 3. So we are going to have A to the power of 4 over 3. So that's it. So the next thing we are going to do is to calculate the section modulus of this section. Section modulus. We are going to calculate the section modulus, and we know that this is denoted with Z1, which is what? I all over what? Y mass. All right. So now we can therefore say Z1 will be equals to our I. Already know that this our I is going to be A to the power of 4 all over 3 divided by our Y mass. Now, the Y mass is going to be depth divided by 2, and the depth of this whole square is going to be from the neutral axis to A is to A, yes, small letter A, and from the neutral axis to C is also what? A. Exactly. So the total distance is going to be 2A, which is the depth. The depth is going to be 2A divided by 2. So we're going to have 2A divided by 2. All right. So this 2 will go with this 2, and therefore this is going to be A to the power of 4 all over 3 multiplied by 1 over A. So A here 1, A here 3. So this is going to be A to the power of 3 divided by 3. So this is what we are going to have. Now, the next thing we are going to do is we are going to find the moment of resistance now. Moment of resistance. All right. And we know that our moment of resistance, denoted with M, is equals to our stress multiplied by the section modulus. All right. So we know that our section modulus here, we'll just use 1 here, and then we can also use 1 here. So this will be equals to M1 will be equals to stress multiplied by our Z1, which is A cubed all over 3. So the final solution is stress A to the power of 3 to the power of 3. So this is the calculation for the moment of resistance of the square section. So the next thing we are going to do now is we want to find the moment of inertia of this new section now, of the section with cut off. You know, said this part with the section, this part out, and this part is out. So that's why I'm using a dotted line to represent it here. So the cutoff section is AEF. We have cut that part out, and we have also cut out GHC. So I will need to write it. Moment of inertia of the new section with cutoff portion. Moment of inertia. Moment of inertia of the new section with cutoff portion. All right. So we can replace that with to be I2. All right. So this I2 is going to be moment of inertia of how many triangles? Now we've cut off this part. So if we cut off this part, close this part, we'll be left with 1, 2, 3, 4. So we are having 4 triangles here minus the moment of inertia of the what? Of the rectangles. So it's going to be moment of inertia of 4 triangles. Of 4 triangles. And what are these 4 triangles? The first triangle is what? Triangle EDK. EDK. And the triangle FLB. FLB. And triangle DKG. Triangle DKG. And the last but not the least is triangle LBH. LB and H. So plus what? Plus the moment of inertia of rectangle of rectangle. The rectangle is what? EFGH. EFGH. So that's it. So this now will be equals to 4 multiplied by the moment of initial of a triangle about the base is what? B h cubed over what? Over 12. Then plus the moment of initial of a rectangle is bd cubed over what? Over 12. So that is it. All right. So, but we are going to look at something critically here. What is the base of this triangle? Of this triangle, you know, this triangle, they are all the same, so we'll just consider one of it. The base is y, and the height is what? The height here, ek, is the same thing as what? Is the same thing as from this point to this point too, which is y. It means this part is the same thing as this part, which is the same thing as this part, which is same for all. So here we are going to have this to be equals to, for the triangle, I'm going to have 4 multiplied by the base is y, and then the height is also y, over what? Over 12, plus, now our base here for rectangle, the base of this rectangle is what? Is EF. Is EF. And if you look at this EF is the same thing as what? Is the same thing as 2a minus 2y. How is it 2a minus 2y? Look at it. From this point to this point, everything there is 2a. And now, we know that from this point to this point is y. From this point to this point is y. So for us to get the length EF here, is going to be the total length 2a. And then when they inscribe the rectangle, from this point to this point is y. From this point, that is y plus y is 2y. So it's going to be 2a minus 2y. So that is why we have 2a minus 2y. Then factor out 2, we are going to have 2 into a minus y, which is the base of the inscribed rectangle. So it's going to be 2. So it's going to be 2 into a minus y. All right. So multiply by the depth of this rectangle. Now let's look at it. This is our rectangle here, EGHF, right? So, and then we know that from this point to this point is y, that is EK is y, and the KG is also y. So it's going to be y plus y, which is what? 2y. So we are going to have 2y cubed here. 2y cubed. All right. So now, let's now simplify. 4 here 1, 4 here 3. So here we are going to have y to the power of 4 all over what? 3, plus here we are going to have 2 to the power of 3 is 8, right? And 8 times 2 is 16. So we are going to have 16 into a minus y. Then we are going to have y to the power of 3 all over what? All over 12. And 4 here is 4. 4 here is 3. So this is going to be y to the power of 4 over 3 plus 4 into a minus y, then multiply by y to the power of 3 all over what? 3. So we are going to clean this side. So you can take screenshot. Further, we are going to have our I2 to be equals to, you know, the LCM here is 3, so we can just open the bracket there. So we are going to have 3 here. Then here we are going to have y to the power of 4 plus 4a y to the power of 3 minus 4 y to the power of 4. All right. I hope you understand. 4 times a times this, 4 times y times this. All right. So here we are going to have this to be equals to y to the power 4 minus 4y to the power 4. So this is 4a y to the power. Okay, I want to maintain my space. Let me just do it here. I'm going to have 4a y to the power of 3 minus 3y to the power of 4 all over 3. So if you split the 3, there you are going to have 4a to the power 3 all divided by what? Let's say over 3 minus y to the power of 4, because 3 will divide this, 3 will divide this. So 3 will cancel out 3 there, then we'll be left with this. So this is our I2, the moment of initial of the new section. All right. So the next thing we are going to do is we'll calculate the section modulus of the new section. Section modulus of new section. All right. So this is going to be Z2. So we know that our section modulus is going to be our modulus of the new section, which is I2 over Y max. So which is 4 a y to the power 3 minus y to the power of 4 divided by our y mass is the depth of the rectangle. The depth of the rectangle divided by 2. The depth of the rectangle is 2y. So it's going to be 2y divided by 2. 2 will go with 2. And again, we are going to be left with 4a y to the power 3 minus y to the power of 4 over y. So if you split y there, we are going to have the section modulus to be 4a y to the power 2 minus y to the power 3. Alright. So this is what, this is supposed to be over 3. Sorry. It's supposed to be over 3. Alright. So that is what we are going to have. Alright. So the next thing we are going to calculate is the moment of resistance of the new section. So moment of resistance of new section. Alright. So we know that our moment of resistance here, since we use M1 for the first one, which is this, so this is going to be M2, and this is going to be equals to stress multiplied by our section modulus, which is Z2. So this is going to be stress multiplied by 4 over 3 ay squared minus what? Y to the power 3. So that is what we are going to have. So we can just put this in bracket. So that is what we are going to have. All right. So the moment of resistance of the new section will be maximum if we differentiate our moment here in respect to what? In respect to y, and we equate it to be equals to what? 0. All right. Take note of that. The moment of resistance of the new section will be maximum if you differentiate the moment in respect to y and we equate it to what? 0. So let's differentiate. So we are going to say d of m2 all over the y will be equals to d all over the y into what? Into our stress into 4 over 3 ay squared minus y cubed. Then you can close your bracket now. So the differentiation of this dm over the y here is going to be equals to 0. So 0 will be equals to, when we differentiate this in respect to y, we are going to have 2 multiplied by 4 over 3. That is 8 over 3 ay. So multiplied by stress is going to be stress into 2, that is 8 over 3 ay minus 3y squared. So that is what we are going to have. So the next thing we are going to do is to if we divide through by our stress, our stress will cancel out, then we can equate what we have inside. So if we divide through by our stress value, so this will go with this. So we are going to have 0 to be equals to 8 over 3 ay to the power of 2 All right. Minus 3 y cubed. Oh, sorry. If we differentiate, we've already differentiate. Sorry. All right. All right. So we are going to have minus y squared here. All right. So we can bring in 3y squared here. I'm going to have 3y squared to be equals to 8ay all over what? 3, right? And y here, we cancel out 1y here. And this 3 will come back here. So we are going to have our y will be equals to 8a all over what? 9. 8a all over 9. So let's call this one to be equation number 1. All right. I hope you understand. You cross multiply. 3 times 3 is 9. And then we are going to be left with 8a here. If you divide both sides by 9, y will be equals to 8a over 9. All right. So now that we have gotten this, we are going to substitute equation 1 into what we have here, into this M2, because we want to check. Don't forget, we are told that and that the moment of resistance is a maximum when y is equals to 8a over 9. So let's check. Maybe it is maximum. All right. So we want to compare maybe M2. The meaning of that is we want to compare maybe M2 will be greater than M1. All right. So here we are going to have M2 will be equals to stress. It's going to be stress into 4 over 3. 4 over 3 multiplied by a multiplied by y. Our y, this y here is y squared. So we are going to have 8a all over 9 all squared. Then minus y cubed. That is 8a all over 9 all cubed. Then we close the bracket. So we are going to say that M2 will be equals to stress into 4 multiplied by a multiplied by 64 a squared all over 9 times 9 is 81. 3 times 81. Then minus 8 to the power of 3 is 512. 8 to power 3. Then this one is 729. All right. So you say 4 times 64 divided by 3 times 81. We are going to have 1.0535. So here we are going to have this to be stress into 1.0535. Then this is going to be a to the power of what? A to the power of 3. Then minus 512 divided by 72. You are going to have this to be 0.7023. 0.7023 a to the power of 3. All right. So if you subtract now, I'm going to have this stress to be. If you subtract this from this, you are going to have this to be 0.35112. Sorry, 12. 0.3512 a to the power of 3. All right. So here we are going to have this to be stress. Let me just write it as stress multiplied by 0.3512 a to the power of 3. All right. So if you look at this value, the value of our M1 here, you can write this value to be 1 divided by 3. 1 divided by 3 is going to give us 0.333. So you can see this. This is 0.35. And this is going to give us 0.3. 0.35 is greater than 0.33. Is that clear? So it means that it is clear that our M2 is greater than what? M1. So M2 is greater than what? Than M1. So it is clear that M2 is maximum when y is equals to 8a over what? Over 9. So we are going to go for percentage increase in the moment of resistance. So I'm going to clean this side. All right, so the first thing we are going to do is to calculate the increase in moment of resistance. Increase in moment of resistance. So this is going to be equals to M2 minus M1. So this is going to be equals to, what is our M2? That is stress multiplied by 0 0.3, 0.3512 a to the power of 3 minus M1. M1, if you divide 1 by 3, you are going to have 0 0.333 okay, stress multiplied by 0 0.333 a to the power 3. All right, so if you subtract, you are going to have this to be nothing but 0.0179 0.0179 a to the power of 3. All right, so that is what we are going to have. All right, so the next thing now is to calculate the percentage increase in moment of resistance. Percentage increase in moment of resistance. So this will be equals to increase in moment of resistance. Increase in moment of resistance all over the original moment of resistance. Of resistance. Then you multiply by 100. Multiply by 100. All right, so that's it. So this will be equals to stress multiplied by 0.0179 a to the power of 3 all over what? All over the original moment of resistance is what we have here. That is stress multiplied by 0.333 a to the power of 3 times 100. So stress will go with stress. A to the power of 3 will go with a to the power of 3. You divide this by this and you multiply by 100. I'm going to have 5.37%. So here is the solution to the above question. I hope it is well simplified and well understood. So if today is your first time coming across our content, don't forget to give this video a thumbs up and don't forget to hit on the subscribe button and also click on the notification bell so that anytime we upload a video like this, you'll be the first to be notified. And don't forget also to join our membership group for you to access premium video such as the one you are watching right now. Thanks.